Okay, so welcome everybody to our usual Wednesday seminars. And today we will hear Kirill Gubarev from the MIPT, who will talk about the Polyvector deformations of supergravity solutions. Kirill?
Yes, thank you for a very nice introduction. And of course, I'd like to start with saying thanks to organizers for such an opportunity to give a talk. And as Sergey said, I will talk about polyvector deformations of supergravity solution. Do you see my laser
We do.
pointer? Okay. I will talk about this topic. This is quite a big part of my work for recent years. It's performed by me, especially Edward Musayev, of course, and some colleagues such as Sergei Barakin, Timofey Petrov, Ilya Bakhmatov, and our Turkish colleagues Nihat Sadik Teger and IBK Katal Ozer. From the very beginning, I would like to start with a motivation and say quite a few words why it is interesting topic for us. For the string theory, it is known that there exist bivector deformations. It is such deformations of 10-dimensional supergravity solutions, which is given by this formula, as you can see. And it is called open closed string map. And firstly, it was discovered by Edward Witten and Nathan Zyberg in their paper on non-commutative string theories. And this formula appeared to be quite useful, and it was realized by these people for the construction of new supergravity solutions. So if in this formula, we will assume for the b-vector parameter beta such killing ansatz, we call it b-killing ansatz. This means that R matrix here, it is a constant antisymmetric matrix, and K are the killing vectors for the initial background that we would like to deform. And we suppose that the starting background of B-field metric and dilaton solves supergravity. Then such a deformation gives new supergravity solutions if the following two conditions are satisfied. They are classical Young-Baxter equation that involves structure constants on the killing vectors, and the so-called unimodularity condition, and we will discuss it a little bit later in details, the meaning of this condition explicitly. Such bivector deformations appeared and called Young-Baxter because they solve Young-Baxter equations, and they appeared to describe integrable deformations of sigma models. It is not shown explicitly that any such deformation preserves integrability of sigma model, but for different examples, it is a known fact. And it is interesting that such a really non-trivial, non-linear deformation has a very nice description in so-called extended field theory. And for 10-dimensional supergravity, it is a double field theory with hidden global symmetry described by the group O1010. And in terms of this hidden symmetry group, this deformation is a local rotation by O1010 matrix. This, of course, we will discuss a little bit later. Various examples of such deformations are integrable, as I said. This means that the sigma models that was integrable before deformation stay integrable after. And we suggested a polyvector analog of these deformations in 11-dimensional supergravity. These are the deformations that give new 11-dimensional supergravity solutions. What questions I would like to address in my talk?
Sorry for interrupting, Kirill. First of all,
Sure. Yes.
can you, so just to understand the Formula One better, what are B's? Just some
B is, yes, it's a B field, Kalb-Ramond field here. G
uh,
is a metric. G is initial metric, the starting metric that solves supergravity equations. Also, B is the solution of supergravity equations. And then we use this starting background, deform it like this, find antisymmetric part of this matrix, it's a new B field, find symmetric part, it's a new metric, and this is the rule how to build a deformed background. You should think about this as a rule to build deformed backgrounds. And we are looking for such betas that give us new solutions. And the answer is known. These are conditions when such a deformation gives solutions.
I see. Thanks. So ten-dimensional supergravity. Can you remind me what is so is this a gauge supergravity?
No, ordinary 10-dimensional maximal supergravity without fermionic part. We of course can include fermions, but for simplicity, I'd like to talk today only about an SNS sector to be clear and honest. But of course, you can involve RR sector, can include fermions and so on. But I will discuss only Navier-Schwarz sector of maximal 10-dimensional supergravity. Okay.
Yeah, so just to be sure, so why it's called by a B vector? Where
yes, why it's called bivector? Because beta has two indices. It has indices beta mn. And we suppose for it B killing indices. So it's bivector because it has two vector indices just. In terms of 11 dimensions, we will have three vectors. For example, deformation. It will have parameter with three indices, and so we will call it.
So you're assuming there are two isometries, so there are two killing vectors.
Yes. At least for performing such a deformation, I assume that I have two killing vectors at least. Yes, you are correct.
Yeah. So then the next question is why the deformed background is solution of supergravity under which conditions? So the claim is that equation of two are enough to preserve solution.
Yes. The equations two restrictions on R matrix are enough for such a deformation to give again a solutions of supergravity. If I started from supergravity solution.
So that means the sigma model, string sigma model, is conformally invariant.
Sure. Yes. Exactly. Yes. And this is why we are interested in such a deformations. This is the way to construct new vacuums, new backgrounds for the field string theory.
Well, this is so that means there should be a way to relate one sigma model to another through some well-defined path integral transformation.
Probably yes, but I would like to stress that it is not equal to T-duality in ordinary string theory. For example, you know that string theory has T-duality, and it is described by group O1010 over the field Z. Yes, but 10-dimensional supergravity has extended group of symmetry. It is O1010R. That means that on some different backgrounds found not from how to say if I find some transformation of background to another background by this O1010 transformation, but which is not over the field Z, but over field R, then the statistical sum of string theory on the first background and on the second won't be the same, because it's not the symmetry of the string stat sum. It is the symmetry of supergravity. So on different backgrounds, string theory will be different on the different backgrounds which we get by this B-vector deformation.
Well, that I don't understand at all, because if you are in an well, there's another question about dilaton.
Yes.
To solution, you need to have non-trivial dilaton.
Yes, I just didn't.
Yeah, okay, sure. But I didn't understand what you're saying about symmetry, because if you just take string theory and pose conformal invariance at one loop, leading order conformal invariance, then you just get supergravity equation.
Exactly. Yes. Yes.
So whatever symmetry is there, it's there. Apart from string theory may have hidden symmetry, which is like if there is integrability, that you'll not see in supergravity.
Yes. Yes. Probably let me say in
maybe best you continue. Yeah, sorry for asking.
Okay. No. It's okay. Interrupt me wherever you want. It is, I think, better when I just talk non-stop about ask questions, please. Let me try to say in other words what I'd like to say. I want to say that on the deformed background, the string spectrum won't be the same. So this deformation of background changes string spectrum somehow. We don't know how, but it is.
Well, that I agree. That's for sure. That's true.
Yes.
That's true for non-abelian duality.
Yes.
It's true even for T-duality, unless you have compactness of the circle, etc. So string spectrum is completely different story.
Yes, and
here is just a local properties which I'm.
Yes, that I'd like to say this because this don't give me any intuition how to make what you suggested about path integral. So I know that the spectrum changes, and it's not obvious for me which transformation I should
again by path integral. For example, non-abelian duality, you can perform this transformation through path integral. It doesn't mean that string spectrum will be the same.
Okay.
So it's just a way to transform one signal into another, and it must exist also. It exists also for this whatever the other Young-Baxter deformations, which dependent Young-Baxter deformations.
I see. I understand what you're suggesting.
Okay. Anyway, maybe best you continue. Yeah. Best.
Okay. The true answer is that I don't know on the path integral side which this corresponds to. That is probably the answer. Okay.
Sorry, may I ask some simple things?
Yes.
Sure. So when you say you have killing vectors, so it means that they preserve G, but they also preserve B.
Also preserve B and also preserve phi. Also, there was a question how dilaton transforms. Let me write it here. Dilaton, I don't remember exactly which degree stands here. This is some number. I don't remember it exactly. If you want, I can find it in article very quickly. The transformation of dilaton is given by this formula. So I know the dilaton at the start. I find how to transform symmetric. I know how its determinant transformed. And so I can find phi tilde from here.
Okay, that's the standard. Yeah, it's the same as in other cases. Yeah, thank you.
Yes.
Yeah, okay, and like another thing, so once you have a background, you have a set of killing tensors, so you have Fij k, right? So this structure constants.
Yes, I have killing algebra.
And then like 2 should be understood as a just system of equations for R, right?
Yes.
Okay, and does it depend on X or?
No, it's constant matrices.
Okay, thank you.
Just numbers. Okay. Which questions I'd like to address in this talk? We firstly for a recent year tried to answer the following questions. We knew B-vector deformations, polyvector deformations in supergravity, and the question was, is it possible to build some kind monovector deformations, and in which theory they will be possible? The answer is that they will be possible in general relativity. And the big question for us, if we can interpret these deformations as some coordinate transformation in extended space. I will explain what it means later, because it is useful for us to understand integrability. If we will understand the deformations, B vector, monovector, polyvector, in terms of deformation, in terms of coordinate transformations in extended space, we will be able to write transformation of Lex pairs and Lex connections. And this seems to be a powerful way to investigate the preservation of integrability under such deformations. And the question is, of course, do such deformations preserve integrability? And from now, my talk will include three big parts. The first part should be considered as a toy model. And it also answers the question how we can build monovector deformations. But it explicitly gives the main ideas of how B vector and 3 and 6 vector deformations built in supergravity. So this will be a toy example where I will explain every step, and we should understand here a logic of the performing a deformation. And after that, I will just generalize this logic on the case of B vectors and polyvectors. For such monovector deformations, I also will show that they generate new solutions of Einstein-Maxwell dilaton theory if the monovector parameter is a Kirill vector of initial background, and I will show that such deformations can be interpreted as diffeomorphisms in extended space, and I will explain what I mean by extended space. And also I will show some examples of the deformations for different backgrounds. So let us start. This toy example is Einstein-Maxwell dilaton theory. This theory is given by such an action, and it is important for us that it is not just any Einstein-Maxwell dilaton theory. It is Einstein-Maxwell dilaton theory with explicit coefficients, 1/2 here, 1/4 here, 2 here. Why it is important for us? It is important because I know that for such an action, there is a hidden symmetry. Explicitly for the case of the D = 3, three-dimensional space, this hidden symmetry is GL4. What does it mean? It means that all this theory can be rewritten in terms of GL4 multiplets. And we know this as the following. We just can write the general relativity in 4-dimensional space and make a KK reduction, Claude-Klein reduction, in the following form. So I suppose for the metric tensor of this theory I will call extended because in terms of this theory it has a new coordinate which I will call Z here. And 4-dimensional space here I will call extended space. Then with such a metric ansatz, from this theory I will obtain this theory if I also suppose that all the fields in this ansatz do not depend on the fourth coordinate. Also let me note that all that I will say will be we can repeat, and we did it for any dimension here. Just you should change some coefficients here to obtain GL D plus 1 hidden symmetry correspondingly. So I have this theory, and now I would like to perform some deformation. So I suggest some method to build a deformation now. How I will build a monovector deformation? I will take the metric G with this end as above, and rotate it by local GL4 transformation, which looks like this one. In terms of Wilbane, it is rotation of Wilbane E by the matrix that makes it not upper triangle. So alpha will appear here somehow. So this generator that appears here makes Wilbane not upper triangle. But I know that in the theory I have local transformations, local Lorentz transformations in flat indices. So I always can apply such a transformation to make the Wilbane upper triangle again after the deformation. Oh, this means that I will call rotated G tilde. I will name its components exactly like this, but with tildes over the fields. Here, 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 here. So I will look at this obtained matrix again in terms of A, phi, and G fields. So then I can write the rule of transformation, how the fields before the deformation and after are connected. In terms of this GL4 matrix, it looks like this. And in terms of components, exactly, it looks like this. This is, you can think about this as a generalization of open-closed string duality. You can think about this as a generalization of this formula, of this one, onto the monovector case. And the statement is that I can look at conditions on alpha that guarantees me that after such a deformation, the phi tilde, A tilde, and J tilde will again solve the Einstein-Maxwell dilaton equations of motion. The sufficient condition is that alpha is a Kirill vector. We just check this explicitly by the fact that the action doesn't transform under such a deformation. For the deformed fields, it has the same value. So this is the rule how the deformation is performed. I have hidden symmetry, then I perform a local rotation of a special form for such a theory, and extract from this the deformation rules. Now I'd like to show some examples that this works and that the deformation is non-trivial. For example, we can take flat D equals 3 space. I didn't wrote metric here because it's obvious, just flat space without any fields. Dilaton is 0 and vector field is also 0. For this space, we have a Kirill vector, which is, for example, boost. And so, performing the deformation by the rules showed above, we obtain the following G tilde, E tilde, and phi tilde. And explicit check shows us that for these fields, the equations of motion are satisfied. You can say probably this deformation is trivial. So I started from the flat background, and after the deformation, I obtained something that is equivalent to the flat background by the gauge transformation and diffeomorphisms. The answer is no. Why? Because I can just calculate Ricci scalar in this three-dimensional theory for the metric G tilde and check the F tilde for the A vector and see that they become not trivial. So on the starting point, this one was 0 and this was 0. Now they are not zeros both. So this is not a gauge transformation from the point of view of this Einstein-Maxwell dilaton theory, not a coordinate transformation, something difficult. More non-trivial example is phenomenological charged black hole of Gibbons-Maeda. It is a black hole with two horizons, and it has a simple Killing vector, which is just rotations around along the angle phi. Performing the deformation for this black hole, we obtain again some difficult solution, but explicit check shows that these fields satisfy equations of motion. Now, the example that is a bridge to the next part of my talk. Let's look at a Schwarzschild black hole in the four-dimensional space. So we take such a metric with f just ordinary expression for the Schwarzschild. And we know that such a solution has, as a previous one, rotation symmetry, rotation Killing vector. And if I perform a deformation monivector along this vector, from the point of view of this four-dimensional space, I will have the following four-dimensional metric. I see that the deformation in this case is very simple, and it is given exactly by change of coordinate phi by this expression. So it's a coordinate transformation. But from the point of view of Einstein-Maxwell dilaton theory, this is non-trivial deformation, because when I will causally reduct now this solution into 3 dimensions, I will see that my Ricci scalar of 3-dimensional metric and the FMN tensor are changed. But this example shows that from the point of view of extended space, yes, from where I started, from this GL4 exactly invariant representation of my theory, I see that such a deformation is just coordinate transformation. And this was our hint for us that probably all such deformations can be interpreted as coordinate transformations in extended space. And that is the next part of my talk. We managed to show this and to see this. From the definition of the monovector deformation, we can extract that the extended space interval transforms like this. And our task was just to find such a coordinate transformation in terms of dx and dz, such that gives exactly this deformation for the interval in terms of 4-dimensional space. And we find out, we managed to, how to say in English, we were lucky to understand that such an expression for the coordinate transformation gives the result that we want. So if I perform such a coordinate transformation, then I will get exactly the same transformation of interval as I get from the monovector deformations. Here I use vector xi. It involves extended coordinate z and Killing vector alpha. And here some details of calculation. I just want to stress here that in calculation it is crucial for us that alpha is a Killing vector of the starting background, and we use it exactly here. So if alpha is a Killing vector, then we obtain that coordinate transformation gives exactly the transformation of interval like this from the extended space point of view.
May I ask you something?
Of course, sure.
Not about this piece, but if you just have gravity,
Okay.
nothing else, like in 4 dimensions, is there a counterpart of this construction? Suppose I have a gravity solution plus Killing vector.
No. Let me answer this question more exactly, because it is probably the main idea of my talk, that to perform such deformations, I need some hidden symmetry in my theory. For example, here for Einstein-Maxwell dilaton theory, I know that the hidden symmetry is exactly this J4 group. And I know that I can recollect my fields in terms of J04 multiplet. And the idea is that I somehow permit all these fields by rotation, local rotation. Here it looks like this. And this is a big idea. If I have only gravity, yes, so I don't have this one, then I don't have such a hidden symmetry, and I don't know how to mix degrees of freedom. So here I have degrees of freedom metric, phi and a, and this hidden symmetry says me how I will mix.
Does it mean that you kind of dress the diffeomorphism, which is a symmetry you're killing, by you like uplift it to a bigger symmetry group, something like this?
Probably yes, but I'm not sure that exactly like you say, but something like that, yes.
It's more like changing the direction of killing just by global transformation.
Yes,
I see.
yes.
Just global transformation. But maybe a small comment is that you can have hidden symmetries just in pure Einstein theory, but it's not that. For example, you can have reduction to 2 dimensions, and then you get some integrable equation that have hidden symmetries, Lux.
Yes. Okay. So I want to say that idea is the following, that I have a hidden symmetry and I try to make local transformations. It is global, but I try to make local transformations and to find which local transformations are, how to say, are possible to obtain the solutions again. That's what I want to say. And for me, it is useful to see here that field bind that corresponds to the parameterization that gives this action. So I obtain again from this action, I obtain this action. If field bind is exactly like this, if I will write A not here and here, then I won't get this action. So the idea of the deformation on in terms of this field bind that I will call generalized field bind is to mix to this field bind a lower triangle parameter. This is the main idea of this monovector, bivector, and polyvector deformations. So I have some reformulation of this theory in terms of, let me say, some gravity here, just ordinary gravity. In the case of 10 dimensions, I will have a double field theory, but it can be thought as gravity as well with some corrections.
Just a second. I suddenly stopped understanding what you're saying. Why you need the Virbind? There is always
I don't need
Virbind. You just need transformation on the metric.
Yes, I don't need, but Virbind shows how to say shows that I can mix to this degrees of freedom some new one. I don't use this I hadn't used this 0. So if I mix to this low triangle parameter, I will have some transformation of this field.
Yeah, but this is just a way. It's just a way of presenting this because
yes.
Transformation is just on the metric.
Yes, it is probably important for me to say that I don't consider such deformations. For example, when this is 0 and this is alpha. Why I don't consider them? Because they just change only A. So this is the transformations of A field. This is the A shifts of A. If this is 0 and this is A somehow. Or when this is not zeros, because this just change E. I want to stress that I exactly look at such a form of deformation because it mixes all phi, E, A very non-trivially, and give some non-trivial transformation, very non-linear for fields. This is idea, to write a transformation that mixes all the fields, not just shifts of the fields, somehow permutates them, mix them with each other. Probably any questions here more? Okay, then let me come back here and let me make some conclusions from the first part of my talk. So we developed a new solution generating technique for Einstein-Maxwell dilaton theory. There exists a lot of other techniques, but this is exactly the new one. We have different examples of such vector deformations, and we showed that if such a deformation performed along a Killing vector, then it generates solutions of the theory. And also important for us that we showed that such deformations can be interpreted as transformation of coordinates in the extended space. Okay, now I would like to move to the more difficult case of bivector deformations. And here I would like to stress again why they are interesting for the community, for us particularly. It is known that the Green-Schwarz string on different backgrounds preserve integrability. And in 90s and early zeros, people were very interested in finding such integrable sigma models of a Green-Schwarz type. And all such examples were connected with somehow were connected with a classical or quantum Young-Baxter equation. So the sigma models that people discovered were integrable if something like this is satisfied for the sigma model parameters. Such deformations of Green-Schwarz strings can be interpreted in terms of the deformations of backgrounds. And the most general way of describing such deformations is exactly bivector deformations that I was talking about in the beginning of my talk. And the natural description of such deformations is given by so-called double field theory. It is an analog of GO4 general relativity for the previous example. Some theory that makes hidden symmetry explicit. And I will talk about this in a few minutes, I think. And it is interesting that such deformations generate solutions of the vector parameters if also for these parameters the classical Young-Baxter equation is satisfied. And this seems to be explicitly it should be explicitly related to this integrability preservation from our point of view. And in the very end of this segment, I will say that bivector deformations also can be interpreted as coordinate transformations in extended space, but now in terms of this double field theory. Let me start with examples of field theories that are integrable. First of all, for integrability of field theory is understood as following. We can rewrite its equations of motion in terms of Lax connection, like this. It is just a generalization of Lax pair for mechanics. And you can show that if such is possible, then you can build infinitely many integrals of motion which are in involution, and so you can solve the field theory explicitly. Now let's just look at some examples. The first and very famous example is the SU2 deformation of the principal chiral model, which was considered by Cherednik. Its action looks like this, and deformation described by ordinary vector J. Such a deformation is integrable for any J. The more known trivial example is the Young-Baxter sigma model with any group G. Its action looks like this, and you can see that all the actions are in Green-Schwarz form of view are formulated. The matrix are here.
What do you mean by Green-Schwarz? Sorry.
That it described in terms of, for example, G can be a supergroup, I want to say like this. In terms of Green-Schwarz, because it describes a string not like a Polyakov action. So it doesn't use explicit, how to say, bulk metric, bulk B-field, bulk dilaton. It just uses some manifold. It can be supersymmetric, and you embed a string into this manifold.
Not sure I understand that, but yeah. So you basically you're trying to say that could be generalized to supergroup.
Yes, and I'd like to say that it is not a Polyakov type of string. It doesn't use any auxiliary metric. It is just embedding of a string into some space. Here it is a group space. Yeah.
Not sure about that. Not sure. What do you mean by that? Not if there's no auxiliary metric, there will be Nambu type action, which will have square root.
Sorry. Green-Schwarz and Nambu type of action is the same for me. One just not supersymmetric, and the second one is supersymmetric. So I think of them as the same. Sorry if probably yes, it's more correct to say that exactly this one is more like Nambu type, of course, yes. What is important here is that such a model is integrable if for this R matrix the ordinary Young-Baxter equation is satisfied. And in a moment we will see that on the supergravity side, this equation will be a classical equation on our matrix R small, which can be understood as the following assumption for the R big. So R small parameterizes R big like this. The most important for theoretics and for us, of course, is integrable deformations and integrability of Mitsayev-Zeitling string. Mitsayev-Zeitling string is a string on the ADS 5 times S5 background. For its description, it uses PSU 224 group because it contains ADS5 and S5, and it is shown here why it contains it. And for the string on such a background in Mitsayev-Zeitling formulation, or in terms of Green-Schwarz string here, it is known that such a string is integrable. It means that you again can construct Lax connection. Equations of motion are formulated in terms of Lax connection, and you can build infinitely many integrals of motion. For such a string, it is known deformation of its deformation is known. It is at the deformation, or Baxter deformation, which looks like this. And it has very interesting properties. The first property, of course, is that such a deformation is integrable, so it preserves integrability of a string on the deformed background. The second one property is that such a string remains kappa invariant. So the kappa symmetry of Green-Schwarz string here is satisfied on the deformed background. And it is very non-trivial that if you extract from this form metric, dilaton, B-field, Ramon-Ramon fields, and try to check supergravity equations for them, that you will understand that they are not satisfied. This was made by these people. And also these people suggested new equations which are solved by background at the deformed ADS5 times S5 background. They called it generalized supergravity. So very non-trivial result from here is that kappa symmetry of Green-Schwarz superstring doesn't require supergravity equations for the string to be kappa invariant. You can relax this equation to the so-called generalized supergravity equations. And so if I mentioned it, let me just show these equations. They are very similar. I only wrote Navier-Schwarz sector, of course, but you can see that they are very similar to ordinary supergravity equations. And we see that they reproduce ordinary supergravity if this parameter I is 0. I here generalizes equation, and it is equations, and it is a Killing vector of the background. So if, again, let me repeat the statement. If such equations are satisfied for the background, then the Green-Schwarz superstring is kappa invariant. And these equations are more relaxed than supergravity equations. This was exactly the way how generalized supergravity was discovered. Now let me talk about the B-vector and Baxter deformations. We would like to look at the string not in terms of Green-Schwarz formulation, but in terms of Polyakov. So I think that I extract from the Green-Schwarz, for example, type of string, exact bulk metric, bulk B-field, bulk dilaton, and I know that these fields for the Ramon Navier-Schwarz string to be consistent, they should to solve ordinary supergravity for it to be Weyl invariant on the quantum level. So I know that these fields should solve supergravity equations. This supergravity is 10-dimensional maximum supergravity, and it possesses hidden symmetry, similar to this case of Einstein-Maxwell dilaton. But now the symmetry is something other. It is ODD group, but we will think always in terms of maximal case when here D is 10. So it will be O10-10 symmetry. What does it mean? It means that supergravity can be rewritten in terms of multiplets of this group again, as it was in Einstein-Maxwell dilaton case. These multiplets are such generalized Wilbane. It is 20 by 20 matrix with 20 curved indices and 20 flat in terms of this group. And it has invariant dilaton. All the theory can be formulated in terms of such called fluxes, and it is formulated as just as a general relativity. So I can build out of these fluxes some analog of Ricci scalar, but for this extended Wilbanes and extended metric, generalized metric. And the consistency of this theory requires some additional condition. This is this one. This condition exactly comes from the following idea. This theory will have diffeomorphism invariance under some generalization of Lie derivative. So this is so-called generalized Lie derivative for the fields in terms of this O10 multiplets. And for this theory to be closed under such diffeomorphisms, we should restrict the field content of the theory like this. Here, eta is invariant O10 metric. It looks like this in O10 form. I'll write it here. And it is 10, 10, 10, 10, 20 by 20 matrix. This matrix eta. And to obtain supergravity,
maybe just small comment to make clear what's going on.
Yes, sure.
So what you're really doing, you're kind of looking at phase space representation, where you have in addition to coordinates xm, you have momenta pm, say.
Yes.
Then you can replace momenta by some extra dual coordinates, whatever.
Yes, windings.
Yeah, and then that's why you have this eta, which is symplectic metric, and
yes,
that's how somehow you double number of dimensions. Yeah.
Yes.
So this is, I'm just trying to.
Yes, you are exactly right. Thank you for your comment. You are exactly right. It is a nice way to understand the multiplication of coordinates. So I just add winding numbers to ordinary coordinates. But this restriction says me that I should choose for each pair. Does I choose coordinate or winding? So string can't wind and extend.
No, it's not correct. You don't need to call them winding. It's not winding. It's just dual coordinates, which are trivial duals of momenta. Yeah, kind of related to momenta. That's all.
Okay. Yes, and for me, it is important that as it was for the case of monovector deformations, I have a theory, supergravity 10-dimensional, and I can write it in terms of this O10 in O10 invariant form, and it corresponds to some parameterization of generalized field bane of so-called double field theory. Now the idea is the following. Oh, sorry, deformation is written here. Again, I rotate my field bine or generalized metric, if you want, by a local transformation, O10 transformation, which looks like this. You can see again that it again includes this upper triangle part here. The field bane is a lower triangle now, and this matrix adds upper triangle parts, deforms my field bane. After that, I can perform a local transformation in local indices to make a field bine a lower triangle again, and this is how I find deformation, how it acts on the field. And if I do like this, I will obtain exactly the formula that was in the beginning of my talk, which is called open-closed string map. So this is, from our point of view, is a nice and natural way to look at this deformation, how it arises, because in terms of double field theory, it is not something difficult like here, difficult nonlinear transformation, yes, but it is just local rotation by O10 matrix. And the statement, as I said in the beginning, is the following, that such a deformation generates new solutions of 10-dimensional supergravity if the following is satisfied. I assume for the B vector B killing NZ, and if our matrix satisfies classical Yang-Baxter equation and the unimodularity condition, then deformation generates new supergravity solutions. Let me stress here that now we can understand the meaning of this unimodularity condition. As we see, this is a killing vector. This is just some coefficient, k, the killing vector, and we can call it just I, some I. And it appears that this I exactly corresponds to the I that appeared in these equations of generalized supergravity. So the statement is the following. If I take this deformation, take from the beginning supergravity solution and deform it by beta that satisfies classical Yang-Baxter equation, but doesn't satisfy unimodularity condition, I will obtain solution, but not of the ordinary 10-dimensional supergravity, but generalized supergravity. And this idea was used by us to reproduce supergravity, generalized supergravity equations from the double field theory equations of motion. So here we see that when I equals not to zero, such deformations also are nice because they preserve kappa invariance of Green-Schwarz, as we discussed earlier. Now, I promised that I will show that such Polyvector deformations can be understood as coordinate transformations in extended space. We not managed to prove this for any bivector deformations, but we succeeded in considering the following special class of bivector deformations. This is a huge class. A lot of examples of bivector deformations for various backgrounds are known, which satisfies these ansatz. So we will assume that bivector can be expressed like two killings P1 and P2. It's something like momenta Q, which commutes with everything, and J something like angular momenta. Only non-trivial commutator for such killing vectors is supposed to be this one, when J commutes with P. And then for such a class, following the logic of monovector deformations, we just succeeded to suggest a coordinate transformation in extended space that reproduces exactly bivector deformations. So we just should take such Xi, that is this combination of killing vectors with extended coordinates x tilde, and then such coordinate transformation reproduces the vector deformation rule for B field G and phi. Now let me make conclusions for this second part of my talk. So there are a lot of integrable sigma models. They form a continuous families. Among them, there is a very interesting example. It is ADS 5 times S5 string, and it's at the deformation. And deformations of such sigma models more naturally can be understood as deformations of backgrounds on which the sigma models live. And the most general way to describe deformations of the backgrounds are bivector deformations. These bivector deformations generate solutions if the bivector parameter solves classical Yang-Baxter equation and unimodularity condition. If unimodularity is not satisfied, we obtain generalized supergravity solutions. Yes, and these bivector deformations can be interpreted as coordinate transformations in the extended space. Okay, now we are ready to move to the third part of my talk, which is about polyvector deformations of 11-dimensional supergravity. So there is extension of bivector deformations in 10-dimensional supergravity to polyvector deformations in 11-dimensional supergravity. These deformations generate new solutions if the deformation parameter solves some generalization of Young-Baxter equation, as we will see. And this is probably somehow connected to the integrability of M theory, M2 brains. And in the end of my talk, I will try to speculate on different connections of polyvector deformations to other fields in theoretical physics, how they can be used for understanding something. And that's all, probably. Yes, I didn't mention that for the construction of polyvector deformations, we will use the analog of double field theory for 11-dimensional supergravity. It is a so-called exceptional field theory. So what is exceptional field theory? In 11 dimensions, supergravity also has hidden symmetries. This symmetry is described by exceptional groups. It is ED symmetries, and we can look at any of it to understand the logic. And let's look at the most simple but most non-trivial one. It is the case of SL5 symmetry. We can split the 11-dimensional supergravity fields, which are metric and free-form, in terms of 7 plus 4-dimensional space. It is exactly KK procedure, Cauchy-Klein procedure, but let me stress here that all these fields that appear here, all these fields, they depend on all 11-dimensional coordinates still. So we use KK reduction procedure, but not suppose that dependence on any coordinates disappear. So it is still full 11-dimensional supergravity, but now in terms of split. It is called a split view of 11-dimensional supergravity. Then such a split has an SL5 symmetry. What does it mean? It means that I can recollect such fields that appeared in SL5 multiplets. So I have just geometric. These 4 vectors are combined with these 6 vectors and become what is called a generalized connection. These scalars and these scalars form generalized Filbine or generalized metric, and these collect into forms. So for this field, now I can write an action which is explicitly a SL5 covariant. And for me, it is important that explicit parameterization of these fields. For example, I wrote here how generalized Filbine should be parameterized in terms of C and metric, but here in terms of Filbines. Filbines are these Filbines are Filbines of this internal metric HRAB. Then concrete parameterization of these fields reproduce this 7 plus 4-dimensional split of 11-dimensional supergravity. Now I think you suppose what will be the logic. I will write some solution of this theory in terms of these fields and perform the signal rotation of the generalized Filbine by local now SL5 transformation. And here it is written in a form that I was using for bivector deformations, and monovector I didn't write here explicit form. It is like this, and the W is contracted with epsilon. Sorry. This is the explicit view for the metrics that I use for the rotation.
Hi, Kirill.
Yes,
I just want to remind that that technically 1 hour is over, but because we had a lot of questions, you have like 10
minutes.
10, 15 seconds, extra spare.
Yes, sure. I will finish in 10 minutes, I think.
Okay.
Thank you for noting me. Okay, and 6 vector deformations will appear in some other extended symmetry groups. So, for example, when I will consider not SL5 but E6 symmetry, and instead of this split, I will consider 5 plus 6 split of 11 dimensions of supergravity. Then I will have E6 symmetry and 5-dimensional deformations will arise. This is just generalization of the open-closed string map. It is called membrane open-closed map, and I will explain its meaning in a few moments. Let me just show which conditions we obtain for this deformation parameters for them to give new supergravity solutions. The linear part look like this. It is a generalization of unimodularity condition in bivector case, and these equations are generalization of classical Yang-Baxter equation. So you can compare these results with this one for the bivectors. It looks very similar. So conclusions are that we can build 11-dimensional supergravity solutions, polyvector deformations, and know when they generate new solutions. So now open questions. The first question is, do such deformations always preserve integrability? And as I said, the first step to understanding this is understanding, is it possible to write after the deformation equations of motion in terms of lax connections? Lax connections are always very difficult. You can look just how they look like for at the deformed ADS5 times S5 case, or just Mitsayev-Zeitman string, and it is difficult to find them. You should have some hint to look for them, and that is why for us it is important that we managed to perform our deformations to understand our deformations in terms of extended space. We now know that they are some coordinate transformations in terms of extended space, and this can be a step and a hint how to build lax connections. So you should just look at how lax connections for the double sigma model transform under such coordinate transformations. Also, the big question is to obtain that also polyvector deformations can be interpreted in terms of extended space diffeomorphisms, and to see this for any case of bivector deformations, not just only for the case that we considered. All this seems to be connected with integrability preservation for the sigma models, and probably know something about integrability of M theory, but these are very difficult questions. The question for us is, can we understand the generalized equation of Yang-Baxter equation from the point of view of some quantum equation? But here are all the problems. We know that tetrahedron equation doesn't correspond to our classical equation because there doesn't exist its classical limit for this tetrahedron equation, and it's a big question to find some quantum analog of generalized Yang-Baxter equation that we obtained. And one of the last questions is how all this is connected to loop algebra and noncommutativity. A quickly remind here is the result of Zyberg and Witten. They considered the string on such a background with G, and B. And they showed that correlator of the endpoints of such a string looks like this. And you can see this beta that appears here. It described exactly by the open-closed map that I showed in my talk. And it corresponds to the noncommutativity. Why? Because if I will look at the commutator of endpoints, I will exactly obtain beta. So beta is a noncommutativity parameter. So the question is, can we interpret 3-vector and 6-vector in 11-dimensional supergravity somehow like this? And the small hint here is the following. If the C field is quite big in M theory, then we can think that M2 brane approximately described by this term. And if we Dirac quantize it and find a commutator for the endpoints of M2 brane, and endpoints here are loops, yes, the endpoints of membrane are some strings, and we suppose that they are closed, then we will see that these loops doesn't commute exactly with the parameter rho. And this parameter rho connected to the background, which appears here exactly by the by this membrane open closed map. It is interesting here to understand not in just the limit of big fields, but for any M2 brane, like it was here. This was exactly full action for the string. Here, just part of the action for M2 brane. And the final question open is the following. We know that M2 branes are naturally described in terms of number mechanics. It was done by these people. Number mechanics generalizes Poisson mechanics as following. It uses generalization of Poisson bracket, which is called number lib bracket, which can be defined through 3-vector parameter, fully anti-commutative. And for this structure, there is a generalization of Jacobi identity. It is a number identity. And it is interesting that this identity, this numberly property of this bracket, exactly gives the equation of on omega that we call generalized Yang-Baxter equation. Interesting steps following here is to use such a description in terms of number mechanics to write some analog of a lax connection idea, some lax connection approach for understanding integrability. But here it should be some 3-dimensional generalization of this idea, and no one knows how to do this. But appearance of these structures seems very interesting and natural. And they, as I said, connected to the generalized Yang-Baxter equation, which looks like a natural generalization of ordinary classical Yang-Baxter equation. And this is very interesting for us.
May I make a small
yes.
comment on this?
Yes, sure.
So there is a recent paper by David Austin. Maybe you saw this.
Yes, I think, but I not don't looked at it quite.
Yeah. So the point of this paper that there is certain limit of supergravity equations in which 11-dimensional supergravity. Well, you need to consider. You need to consider M2 brane wrapped on a torus in certain supergravity background, which could be, for example, ADS3 S3 times T5, something like that.
Okay.
Then in a limit of large number of wrappings over the torus, when membrane wraps over 2 torus, or maybe actually 3 torus, Euclidean. He claims that the equations for the membrane they reduce to Mikhailov-Monakov, I think, something like that. There's a system which is a limit of self-dual Young-Mills plus scalar, which is integrable in 3 dimensions. It's not Lorentz invariant, but it's integrable in 3 dimensions.
Mm-hmm.
So yeah, but this is quite artificial, but there is another case where integrability kind of appears.
Yes, it.
But I'm not sure it's related to this. That will be interesting if it's.
No, thank you. It's very interesting. I will definitely look at this paper closely. I saw it, but I hadn't time. So I see to look at it closely. But now I definitely will. Thank you very much for suggestion. Yes, but for us it's very interesting, of course, because we see and believe that all this somehow connected to three-dimensional integrability, and understanding of it is very, very intriguing question for nowadays. I think like this. And also, sorry, I forgot about the last question, but I can say very quickly about it. We know that there is a holography, so there is a correspondence between gravity or supergravity with quantum field theories or super conformal field theories. And we can think about the deformations that I talked about from this holography point of view, and all the deformations that we discussed should somehow be connected to the deformations on the field conformal field theory side of view, and different deformations along IDS or along M will correspond to addition of some operators or changing some vacuum values of some operators, changing of Renor group behaviors, adding some noncommutativity, as we saw, to conformal field theories. And this seems to be very, very interesting, because it is another way to use such deformations to investigate the dual conformal field theories, their properties, so that they have some operators interesting, marginal, for example, or something like that. They can be made non-commutative. And now that is all that I wanted to say. Thank you very much for listening, and very interesting questions. And if you have more questions, ask. I will try to answer.
Looks like our organizer disappeared. Mitya,
Okay.
maybe you take over, Mitya.
Yeah, okay, so yeah, I don't know. It seems that there are no further questions, right?
Yes, and are there any questions? No. Okay, sorry. I was AFK for 1 minute.
No, okay, yes.
So, okay, if there are no further questions.
Excuse me, can I ask a question?
Yes.
Sure, yes.
Here, you hear me. I just, it's first time that I see the 3 bracket, plus on 3 bracket. Can you explain for the amateurs, is this the object which appears in some kind of Hamiltonian equations, or?
Yes. Okay, let me say a few words about this. There is a generalization of Hamiltonian mechanics. It's called Nambu mechanics. It uses 2 Hamiltonians for evolution. For the description of evolution, you need now 2 Hamiltonians, H1 and H2. And you describe evolution of your physical system by generalization of Hamiltonian equation, something like this. I probably write not exactly coefficients here, but this is just generalization of Hamiltonian equations for Nambu mechanics. And for example, 2-dimensional harmonic oscillator possess such a description. You can formulate a two-dimensional harmonic oscillator in terms of Nambu mechanics, reproduce correct physical solutions, motions of it. So this is the simplest example that possess Nambu mechanics. Another interesting example for us of a system, it is M2 brain. M2 brain, exactly two M2 brains. That was done by these people, by Lambert and Gustafsson. So they describe the mechanics of M2 brain in terms of this number mechanics.
Okay, thank you. Okay, can I ask a stupid question? M2 brain means that it is 1 plus 1 dimensional, right?
One plus
time,
one.
space.
No.
2 plus 1. 2 plus 1.
Yes, it's
to space.
Yes. There is a suggestion suggested by Townsend, if I am correct, that when you talk about brain and the right number here, it is a number of spatial dimensions.
Okay. Yeah. So the coordinates of this brain are functions of three coordinates. So.
Yes, but in space-time, of course, its world volume is three-dimensional. In fixed moment of time, it is two-dimensional. In fixed moment, but its world volume.
What I wanted to ask, just a stupid question, is that in mechanics you have a function of time equal to the three bracket with the Hamiltonians, and here.
Sorry, which bracket? I didn't get.
No, three bracket in mechanics, in three bracket mechanics, that as you explained. So here you have a function of space and time, and Hamiltonians are functionals, right?
Yes.
Okay. Usual stuff. Okay, yes. Thank you.
And the idea is that you know the theory on some spatial slice. You know two Hamiltonians, and you can move in time direction from this slice to any other slice in time.
And the point is that there is no just usual Hamiltonian is absent.
Yes. The main statement is that no all Nambu systems, so not all the systems that are described by Nambu mechanics, can be reformulated in terms of Poisson usual Hamiltonian mechanics. For example, two-dimensional oscillator, harmonic oscillator, has both descriptions, and Nambu and usual Hamiltonian one. But for example, M2 brain don't.
Okay. Thank you very much.
Okay.
Thank you for questions.
Yes. Okay. If there are no further questions, then let us conclude. Okay. So thank you for your talk, Kirill, and we hope to hear you again soon.
Thank you very much for your invitation and attention and nice questions.
Thank you.
Glad to appear at the seminar again.